So what do we actually do with these loop laws? Because it might not seem very useful yet. So this is a really important tactic, and I'm going to go through the tactics box that is in the book, and then we're going to look at some examples. So the first step is that you need to have your circuit diagram. So this is a big part of your representation. So any circuit problem, if it's been described to you or what, you need to draw a circuit diagram. If you've been provided with a circuit diagram, then part of your visual representation will actually be doing this analysis. Note that here it uses the word draw. There are going to be places that you really want to be able to actually label these things, and when you make equivalent circuits, such as using equivalent capacitors or equivalent resistors, you probably want to draw new circuits that use those. So make sure that when you have a circuit diagram, you've labeled everything. That might be in terms of variables like R1, R2, C1, C2, or it might be specific values like 10 ohms or 10 picofarads, or it could even be both. That in some cases you might want to manipulate the equations in terms of variables and only plug in values at the end. So the second step is going to be assigning a direction to the current. Note that the word here is assign. So if all else fails, you might actually pick the wrong answer, but in the end your answer will tell you that. So it says if you know the actual current direction, choose that direction. So one of the obvious ways that this happens is, for instance, you have the positive terminal of a battery. Well, in that case, assuming that there's actually a circuit here with some stuff happening, you would say that I flows from the positive terminal of the battery. Now remember that even though electrons are our charge carriers, we say that the current direction corresponds to positive charges flowing. Now, something that might happen is that you might not know the actual current direction. And the reason that might happen is you might have more than one battery in your circuit, and they might be oriented in different ways. So here they say, well, what if your choice is wrong? Well, you'll end up with a negative value of I, so that just says that it's flowing the opposite way. So in that case, it's not really wrong. It's just that you've chosen one direction to be positive and the current you've gotten was actually flowing the other way. So if you have any indication of what direction it is, pick that direction. But if you choose the opposite direction, there's no problem with that. So the next step is the one that we need to do some examples of, which is traveling around the loop. And that's again the idea of trying to go in a complete loop and getting that the sum of your delta V is equal 0. Now note that we're always talking about delta V. Sometimes we're going to be labeling specific points, and that's what it's talking about here. So as you're going through the loop, that sometimes you're going to have a circuit element, and instead of specifically having a delta V, you might know that this point is 2 volts and this point is 6 volts. Well, what is your delta V? Your delta V, when it says downstream minus upstream, that's going to be negative 4 volts. That was not a V, negative 4 volts. So again, with practice, this is going to make more sense, and especially as you work with batteries and different orientations, this is something to be very careful about. So in the case of batteries, we need to think about differently if you're traveling from the negative to the positive versus the positive to the negative. So again, when you're traveling, you always need to have a direction that you're going in your loop. You're not just picking all of the components in the loop, but you're specifically going in a direction. And so if you go from negative to positive, your delta V is the EMF of your battery. Note that by saying this, we are assuming that this is an ideal battery, and that's in general what we always say. So that's okay. So ideal battery, we get to just use that our EMF is equal to the delta V. Now, on the other hand, if we're going from positive to negative, remembering that the direction of travel matters, now it looks like your battery is actually taking away potential, right? So now we actually have negative E. And this is important because you are going to see circuits where this is set up. Now, it isn't actually very useful in a real circuit to do this, so some of this is for practice. On the other hand, you can have real circuits that have more than one voltage source in them, but depending on how you choose your loop, you may have some of them oriented backwards. So again, seeing this in context will make a little more sense, but do remember that the way you're traveling across your battery actually matters. Now then, we get to our resistor. Now, what's tricky about our resistor is that we need to be going with the current for this to work. So as long as we're going with the current, we get to say that the potential on one side of the battery is higher than the potential on the side of the resistor you're starting with is higher than the potential on the side you get to. And so it's negative IR, where that's just coming from Ohm's law. But if your loop is actually reverse of your current, that won't work. So that's why step 2, remember step 2 up here, was define the direction of current. So if you have a resistor where you say your current is going that way, but as you travel through your loop, it goes that way, well, in that case, you're actually adding potential because you see that you're going reverse of the current. So make sure that you think about the current direction when you have a resistor, and it makes the most sense if your loop, which is the direction of travel, actually goes the same direction as your current, but there will be some situations where that doesn't happen. Now the final step is to say that all of these delta V's all around your loop actually add up to 0. And keep in mind that the reason we would be doing this is, for instance, to find a specific value of R, or to find a specific value of I, or to find a specific delta V across the component. Maybe there's an unknown battery EMF. So if you have, depending on what you actually know, you might be asked to find a missing value. So that's why you do this in the end. If every single thing was known, then this works out to be true, but in general, there's some missing quantity that you're trying to find.